This video covers the first section of Chapter 7, which I think is a pretty interesting connection between experiments and some concepts that you've seen before. The quality of the instrumentation is really important, as I think you'll see, and that's can be a hang-up in doing conductivity measurements in an undergrad lab. I think Dr. Breen may have planned for you guys to do a conductivity measurement. I don't recall off the top of my head. But anyway, here's the theory behind it and some applications. So our last chapter of this semester is looking at electrolyte solutions. So as I say here, all biological systems, I'm sure you know this, and many chemical systems have ions in the solution. In Gen Chem, you study a lot with acids and bases and salts. And you know that those compounds are called electrolytes if they introduce conductivity into a solvent. So remember earlier we discussed a concept. It was from the kinetics chapter. It was called ionic strength. I wrote down the page number here, 706. That was actually ended up being a foreshadowing of the huge effect that ions have on the properties of a reaction. You might recall that rate constants can really change quite a bit. I remember kind of an image that looks something like this, depending on what the values of the cations and the anions were that were in the reaction. So you could have huge effects on kinetics if there are ions present. So in order to do this chapter, we need to learn or perhaps relearn some important vocabulary. So you might remember from physics that current is the flow of charged species, and the capital letter I represents current flowing through some medium. Now we're talking about current flowing through a solution, so we'll talk about charged species and the effect ultimately that the solvent has. I've tried to stick to a consistent color code here where I have the units written in red. So the units of current are amps, sometimes represented by a capital A, and the current is the potential difference between, you can imagine, two electrodes I have sketched at the bottom and measured in volts, and the resistance is in the denominator, and that's going to be in ohms. And you might remember, again, Ohm's law written this way from general physics. Well, the resistance of the medium is going to depend, I shouldn't say the resistance of the medium, the resistance that the current faces depends on the geometry of the electrodes in the cell. And so you could see my little sketch here. I have kind of two rectangular electrodes. The cross-sectional area of the medium, so essentially the slab of solvent that's in between those two electrodes, if you slice through it and got that cross-sectional area, that's the capital A in the denominator here. So I don't mean to confuse you, but the A for amps is a different A. That's actually more of an abbreviation rather than a variable. This is the actual measurement. The L on the top is the distance between the two electrodes. So that ratio is called the cell constant. And in order to get that value, you're going to have to run your experiment with a known standard. We didn't quite get to that point yet. But so where were we talking about here? We were saying that the resistance that the current faces is going to be proportional to this thing called the cell constant. Now a constant, I shouldn't say a constant term, a proportionality factor is called the resistivity. I use the Greek letter rho here. You're going to see a lot of Greek letters in this chapter. The Greek letter rho has units of ohm meters or ohm centimeters, depending on the cross-sectional area value. So the resistance is going to be proportional to this thing called the resistivity. A more old-fashioned descriptor of that term is called the specific resistance, and it's going to be a property of the medium. So the same pair of electrodes, of course, are going to have a different resistivity if they're in water compared to ethanol, let's say. In the field of electrochemistry, people tend to be a little bit more positive, no pun intended, about the properties of conducting charges. So it's normally conductance that gets measured, not resistance. That seems kind of negative. So I kind of string together the equivalences here. So usually you have a a conductance meter, although we often call it a conductivity meter, and you can see that there's some confusion there. You really have to be careful with what letters and what units you're using. So the conductance of a solution is the inverse of the resistance. The units of conductance are Siemens or inverse ohms. And we already had an expression for resistance, and now we're introducing a new expression for the inverse of the resistivity, which is called the conductivity, sort of the positive version of resistivity. The old-fashioned name is called the specific conductance. If you work through the units, I'm sure you can, you're going to get inverse ohms, inverse centimeters, or inverse ohms or inverse meters. As I mentioned earlier that the cell constant was L over A, and you need to calibrate that by measuring the conductance with some standard solution of usually potassium chloride. Now, in order to compare different electrolytes, it's best to compare them by their molar conductance. It's not really fair to say, oh, this solution conducts twice as much as another solution if you have twice as much salt dissolved in it. That doesn't seem fair. So this is kind of the molar version of this property. So you take the conductivity from 7.3 and you divide it by the concentration of the analyte. Again, I want to point out that unless you're careful, you can easily make mistakes. This C is a lowercase c for concentration. The capital C above for conductance should not be confused. So this letter is another Greek letter. This is a capital lambda. Lambda. Basically the capital version of what you know from wavelength in Gen Chem, but we don't need to talk about wavelength. So the molar conductance is represented by lambda. Again, if you work through the units, you'll see that this is inverse ohms, inverse moles times centimeters squared, because the concentration is a distance cubed, and if you remember from up above, you've got a distance in the denominator, so that's how you end up with a distance squared in the numerator. All right, so now we've basically walked through something called molar conductance. So you've got these electrolytic solutions, and you want to measure how good they are at conducting charge. So here's a couple of examples just to go through the equations we've discussed. So if you're given a solution and the conductance, the capital C, is 0.689 inverse ohms, calculate the conductivity if the cell constant is given to you. Well, you're going to see equation 7.3 from the previous slide, and you could solve for kappa very easily. By the way, another Greek letter, kappa, the conductivity. You got a value of 0.176 inverse ohms, inverse centimeters. Example 7.2 gives you the conductance for a potassium chloride solution. So you have a 0.0560 molar solution of potassium chloride. Now, if the same cell is filled with sodium chloride of a concentration of 0.0836, and that conductance is 0.0285, calculate the molar conductivity of the salt solution, given the molar conductivity of the potassium chloride solution. Careful again, capital C is different than little c. Well, first you need to use the potassium chloride data to get the cell constant. And you rearrange equation 7.4, solve for kappa, you get 7.53 times 10 to the minus third, plug that into the equation from above, the start calculation 7.3, and you can get the cell constant is 0.315 inverse centimeters. Now that you know the cell constant, you can apply the characteristics of that cell to the new solution, which is sodium chloride. So I go back to my kappa equation, and I solve for it in the sodium chloride solution, and then the molar conductivity, I get a value of 107 inverse ohms, inverse moles, centimeters squared. Notice that I needed to do a conversion in here because the concentration was given in terms of molarity. If you remember molarity is moles per liter or moles per decimeter cubed. So if you want to convert into centimeters, which this usually does, you need to make that conversion. All right. So when looking at the molar conductivity, it may appear that molar conductance, I said molar conductivity, molar conductance may be a pure intensive property of the substance. It doesn't depend on how much you have, because if you're dividing by concentration. But it turns out in reality, plots of the molar conductance do vary with concentration. Now, why would that be? Well, think about what's going on in a solution. You're talking about charge moving through the solvent. If there are other ionic entities around, you can imagine, can't you, that those can sort of hold you back or even aid you flowing through the solution. So molar conductance actually does vary at higher concentrations. The fellow who did these measurements, it was at the end of the 19th century actually, was this fellow named Kohlrausch. And Kohlrausch saw that if a plot of molar conductance versus the square root of concentration gave these variations. They kind of have some interesting characteristics. I noticed that the acids here seem to bend or vary more. That could be a clue to something. Here we have some different salts, and you notice that it appears that potassium seems to conduct better than sodium. That could be interesting. And then finally we have a weak electrolyte at the bottom. Not surprisingly, you might think that since something like that only partially dissociates, you're not going to get as good conductivity. Another thing that is interesting about the weak electrolyte, notice this sort of asymptotic approach there. There's kind of a really sharp fall off as the concentration gets a little bit larger. That ends up being kind of problematic for getting good data. As I say here, the intersection of these lines with the y-axis, this is called the molar conductance at infinite dilution. It's basically an extrapolation of the line taken at different concentrations, and you can be pretty accurate for most things, but it says it's not as good for weak electrolytes because of that asymptotic approach. It can be difficult to very accurately get the place where it's going to hit the line, or at least it's going to be less accurate than the other ones. I think you could buy that. If you look at table 7.1, you've got some data for these what I'm calling these molar conductances at infinite dilution. That's what the little aught is, the little naught that I just drew. That's this intersection of the line on the left. There's a pattern that emerges if you looked at the numbers carefully and kind of manipulated them for a little bit. And here's what happens. If you take the two values for potassium chloride and sodium chloride, and then you look at the two values for potassium nitrate and sodium nitrate, you see that the differences between the two are exactly the same. Kohlrausch thought, you know what? What's going on here? It must have something to do with the fact that although the anion is constant, I'm changing the same cation, or I'm replacing the cation with the same cation in each of these sequences. What he then thought is, oh, if this has to do with salts conducting charge through the solution, maybe each ion has its own conductance. And this is what he proposed, essentially equation 7.6, that the overall molar conductance at infinite dilution was going to be a sum of the contribution of each of the ions. The little nu here, another Greek letter, that's the number of ions of that type. And the lambda, the lowercase l, lowercase Greek l, that's the molar conductance of that ion. So if I had sodium chloride, I would just have the molar conductance of a sodium ion and a chloride ion separately. If I had, let's say, sodium sulfate, I'd have 2 times the conductivity of a sodium and 1 times the conductivity of the sulfate. Take a look at a little bit of derivation here. So equation 7.6 that I just wrote is called the law of independent migration. And I reproduced it here. Now you can see why the pattern emerged that we talked about before. Because if each salt has its own contribution, separate contribution from the cation and the anion, and you multiply all those out, you can see there's some canceling going on, and these two values end up being exactly the same. So some clever additions and subtractions, you can get some data, and table 7.2 shows the table of those values. Now Arrhenius, you've heard of before, he was the 19th century chemist that formalized our understanding of acidity and basicity. Basically, he gave the first definition of acids and bases. He also did echem experiments that verified some of his ideas. For example, he figured out that if you took conductivity measurements, or really I should say conductance measurements, on weak acids, they could lead you to equilibrium constants. And what's a weak acid without an equilibrium constant? Not very interesting, I say. Basically, he came up with this expression that this alpha here is the degree of dissociation of the weak acid. Basically, it's a ratio between the measured value of the conductance compared to what it would be if it was an ideal value or at infinite dilution. In other words, that the weak acid totally dissociated. So you can imagine, can't you, that if I have 10 molecules of weak acid, let's say, and only 1 in 10 separates, whatever that conductance is going to be 1/10 compared to the salt completely dissociating, or the weak acid completely dissociating. So this is a very sensible ratio. Again, it's the degree of dissociation of a weak acid. It's the measured value divided by the ideal value, or the infinite dilute value. So you can get this Ka value by doing a plot of different concentrations. I'm sure you remember from General Chem, depending on what the concentration is, there's going to be a different percent dissociation. So here's the derivation that Ostwald did. He basically defined the weak acid almost like a version of an ice table, in which you have some initial concentration, and the degree of dissociation is going to be the fraction that dissociates. So those are the little alphas. Now the definition of a weak acid constant is the product values divided by the reactants, and you could see that you could do some substitution and then substitution and rearrangement here, and that's what goes on. So I substituted in the definition of what alpha was and expressed it in these equations. I basically want to rearrange this sort of messy looking thing so that I could get something that's convenient in the form of a straight line. And so I multiplied out this denominator with the Ka, and then divided by made a couple different divisions to get eventually the equation in red, the Ostwald dilution law. Here, as you can see in the graph I sketched, that if you take 1 over the measured conductance, the molar conductance, and plot it versus the concentration times the molar conductance, that's basically calling this the y, and then the x is over here with the slope, the slope being this term, the 1 over Ka infinite dilution value squared. So getting in a weak acid constant with some very simple measurements with a good conductance meter can allow you to get some data. There's an example in the text I'd like you to do, 7.3. Let me see what I have here. Yeah, basically they're just asking you to basically plug in some numbers to get Ka. You don't have to do a plot for 7.3, but you can see how to do a plot. It's very straightforward. Okay, so we were just talking about how Kohlrausch felt that the contribution to the conductance can be separated out into the contribution from the cation and the contribution from the anion. As we saw, though, depending on how many ions are in solution, that can slow down the flow of the ions. So now we're introducing a concept that we're going to try to get a handle on measuring this flow. Not just the carry of charge, how much charge can flow through the solution, literally how fast or how mobile are the ions in the solution. So as I say here, molar conductance is going to depend on the ease of ionic movement. Remember, they moved faster when it was very, very dilute. As more ions come along, it slows them down. Now, ionic velocity, you could attach the word velocity to speed, right? And that speed, though, is going to be dependent on whatever the field strength is. So if you remember my little sketch earlier of the conductance device, how strong the voltage, how high the voltage is going to affect how fast they go. So if you could take the voltage and divide by the separation of the electrodes, you can get a velocity. Now, on the other hand, that velocity number, that's just a raw number. You're seeing basically this cation just flying through a solution. On the other hand, ionic mobility is a way to eliminate the field effect. What's the inherent mobility of an ion? So you would take the velocity value divided by the field and get the ionic mobility. Here they use just the letter U to represent that. So equation 710 is saying that the ionic mobility of a cation is the velocity of that cation divided by the field. I've got the units reproduced here on the right. This ionic mobility is related to the molar ionic conductance. The units can, you can work that through by looking at the units. And so the ionic, the ionic conductance, let me get that term right, my little lambda. Yeah, the molar ionic conductance divided by a constant called the Faraday constant, that's the charge of 1 mole of electrons, gets you the mobilities. Those values are also present in 7.2. So the table I mentioned earlier has ionic mobility values. One of the things you'll notice when you look at that table, there's a distinct increase in mobility for the hydrogen cation and the hydroxide anion. There's a little mechanism in the book that emphasizes for you that the fact that water is the solvent is a big part of this. And what we end up seeing actually is that the proton that's flying through solution is not literally the same proton covering a big distance as, let's say, a sodium ion is. If you have an electrode that's charged negative here, when you're talking about ionic mobility, you're talking about an individual sodium ion flying through the solution. That isn't what happens with water. It's kind of like a big game of telephone where the proton from at the beginning is going to pop into a water molecule, and that's going to give up another proton, and so on, and so on, and so on. It's like kind of a domino effect. And that domino effect can be much faster than an individual ion flying through a solution. Here's an example with the equations that you've just been presented. If you're given the ionic mobility for a chloride ion at 25 degrees, calculate its ionic conductance. Pretty straightforward. You're going to calculate the, basically rearrange the equation I already showed you. You have the Faraday times its ionic mobility, and then basically what remains is kind of a unit change. A coulomb, I really should have drawn that as a bigger C. A coulomb per second is the same as an amp, and then an amp divided by a volt is an inverse ohm. So you could clean up the units a little bit with those two substitutions. You could also calculate how much time it would travel for a chloride ion to travel from one electrode to another, in this case 4 centimeters if the field strength is 20 volts per centimeter. So first you're going to calculate the velocity. That equation was from 710. Once you get the velocity, that's a distance per time, you could rearrange the solve for time. And it turns out that 4.2 minutes is going to be the time that it takes for an individual chloride ion to go 4 centimeters under that field condition. The last application I have is acid-base titrations. In intro chem, when you did acid-base titrations, you either used a pH meter or a colored indicator to give you information about when you had reached the equivalence point. You could do conductance measurements to figure out when you got the equivalence point, and we'll talk about a couple of examples here. So first things first, look in red. I have a steeply falling conductance measurement as I'm adding the sodium hydroxide. Basically, the reason is, as I say in my little essay here, I'm essentially replacing H plus ions with sodium ions. In the strong acid, strong base titration, as the sodium hydroxide is being introduced, it's forming water, and then the spectator, sodium, is not as mobile. for the reasons we had already said, that sodium is being part of the, for hydrogen ions being part of the solvent, their conductance contribution is going to be much bigger. So as you're adding the sodium hydroxide, you're lowering the conductance of the solution until you reach the equivalence point. Once you reach the equivalence point, you're just adding basically 2 ions, you're adding 2 ions for every formula unit, and so the conductance, as you might expect, is going up very steeply. In fact, I probably should have drawn it more steep than the HCl was going down. For the weak acid strong base titration, we have another interesting result. Now, I assume that I was starting with the same concentration of acid, so the equivalence point is going to be at the same volume of sodium hydroxide added. But look what happens, how the conductance increases from the beginning and goes up more sharply after the equivalence point. So if I have a weak acid, like let's say HA here, and water in equilibrium with H3O plus and OH minus, the conductivity is actually going to go up as I'm adding sodium hydroxide. And why is that? Because the hydroxide is going to neutralize the H3O plus, but all that will do, since this is a weak acid, will cause a shift in the equilibrium, a la Chatelier, and so I'm going to basically replace the ion that was there immediately. However, there's a net increase in ions because I'm adding sodium as well. I'm not really replacing an H3O plus with a sodium because the H3O plus gets substituted. It gets replaced, I should say, by the source of acid on the left. So that's why the conductivity goes up slowly during a weak acid titration. Once I reach the equivalence point, though, and there's no weak acid left, all I'm doing is adding a bunch of ions to the solution, and as you might expect, I'm going to get a very sharp increase in the conductance. I forgot this application, the solubility determination, another quantity you've seen before. This is for, let's say, a KSP, for a sparingly soluble salt. So suppose I say a sparingly soluble salt is added to water, and you could think of, let's say, silver chloride. When you place it in solution, some of the ions, not very many, go into solution. Well, I'm going to rearrange equation 7.4, that's the one for the molar solubility, and realize that whatever the concentration is of the species in the solution, that is going to be equal to the molar solubility in this context. So really, little c and capital S are the same thing in this context. Because that capital S is going to be really small, it's a sparingly soluble salt after all, we're going to assume that the measured value of the molar conductivity is going to be the same as the infinitely dilute version, because again, it's very, very small concentration. And so I get this expression right here. Experimentally, it's shown that for silver chloride, you can get your kappa value of 1.86. Now, when you take a measurement of a salt in the solvent, you have to subtract any contribution from the solvent. Remember that water has a very tiny auto-dissociation, so you need to subtract out the little bit of ion contribution that it has, and this actually ends up being your kappa value. So if you go to table 7.1, you can get the infinitely dilute version of the silver chloride, and we do put those into the equation, account for the fact that we have kind of a mismatch in units here, and I threw in my, where did that mismatch come from? Oh, because I want solubility in terms of moles per liter. And so I get 1.3 times 10 to the minus fifth for the capital S. The KSP is just, in this case, simply going to be the silver concentration times the chloride concentration, and so for that, I get a value of 1.7 times 10 to the minus 10. There's a few little exercises at the end of Chapter 7 I'd like you to do, and this was kind of fun. I will see you on Wednesday.